So one of the easiest function to optimize is a quadratic. So we'll start over there, right? So what if j of s is a quadratic, right? Is equal to as squared plus bs plus c. Okay, so in such a case, when s is a quadratic, how do we minimize or maximize this objective function? How do we find out what parameter value should we choose in order to maximize or minimize this objective function? Well, in the case of quadratic, it's actually pretty simple. If a is positive, okay, so there are two cases. If a is positive, we know that the quadratic looks something like this, right? It increases to infinity as s approaches either plus or minus infinity, and it has a minimum. So we can only solve the minimization problem of j, and this is given. This can be solved by taking this derivative, by taking dj ds equal to 0. That is this minimization point. And we know the advantage, the reason a quadratic is the easiest to optimize is that when you take derivative of a quadratic function, what does it become? The derivative becomes a linear function of s, right? So dj ds equal to 0 is going to give us a linear equation. So 2as plus b equal to 0, and we can solve it. We get the minimizing point of this quadratic. Correspondingly, if a is less than 0, we can solve the maximization problem. And it can be solved with the same equation, the derivative equal to 0, which means that still we are going to get a extrema, but just in this case, the extrema is the maximum of the quadratic. Okay, so this looks very simple, right? And but this is really most fundamental building block of many different optimization methods. So to go to the next level, let's now consider a multivariate quadratic as opposed to a univariate quadratic. So what is a multivariate quadratic like? A multivariate quadratic, j as a function of s. Now s is a vector. All right, and this quadratic actually involves all kinds of quadratic terms of s. In order to express it, we usually write it as still a constant term, just like our univariate, still a linear term, but in this case, the linear term is written as a b transpose times x. So s is a vector. If I write it as s1, it's actually to sn, then this v is a correspondingly long vector containing the linear coefficients on every single one of these design variables. Now comes the quadratic term. In the multivariate quadratic, the quadratic term can be written as a very similar form as the one-dimensional case, except for I have to write it in a matrix form. The matrix form is S transpose times a matrix times S. Okay, so the A, where A is a symmetric matrix, why is A symmetric matrix? This is because if A is not symmetric, then I can write a equivalent matrix A that is symmetric and represent the same, exactly the same quadratic function. right? Consider the 1, 2 term of A. If the 1, 2 term is different from the 2, 1 term, then what happens? The quadratic term has basically has a S1 times S2 times A12, right? Plus S1 times S2 times A21. So if you take the average of A21 and A12 and put that average in both the 1, 2 location of the matrix A and the 2, 1 location of the matrix A, you're going to get the same quadratic. So in general, we can use a symmetric matrix to represent this quadratic term. Okay, and so if you look at this matrix form and wonder what is the parameter S, what is the vector parameter S that is going to maximize or minimize the quadratic, we can use the same formula, right? We can use the same formula by taking now the partial derivative of J with respect to S equal to 0. So the partial derivative equal to 0 means the derivative of J with respect to every single one of Si has to equal to 0. This is really the optimality condition. We call the first order optimality condition. Of this quadratic.